Exercise 2, parametric parabola, tangents and normals. So here are a couple of HSC style questions. Number 1, the normal at the point P, 4P, 2P squared on the parabola x squared equals 8y intersects the y-axis at Q. Find 1, the equation of the normal in parametric form, 2, the coordinates of Q in terms of P, and 3, the equation of the locus of the midpoint of PQ in Cartesian form. Alright, just pause the video and have a go at this one. Alright, now in part 1, what I'll do, I'll just draw a little sketch first, just give a rough idea what's happening. So we've got a parabola here, like that, and we've got this normal here at P. So the normal goes through like that. Whoops. There we go. And it's going to intersect the y-axis at Q. Okay. And we're going to find the equation, the locus of the midpoint of PQ. So we have to find the coordinates of that. It's our final thing in part 3. Alright, okay. So let's get the equation of the normal going first. Right, now we know that x is equal to 4p, and we know that y equals 2p squared. So integrating that with, differentiating that with respect to p, we get dx dp is equal to 4, and dy dp equals 4p. Using the chain rule, dy dx equals dy dp times dp dx, which equals 4p times the reciprocal of this one, 1 on 4, which again equals just p. Okay, now putting in the point gradient form, we get y minus 2p squared equals, now this gradient here is the gradient of the tangent, so the gradient of the normal with the negative reciprocal, so that's minus 1 on p into x minus 4p. So y minus 2p squared equals minus 1 on p x plus, now if we multiply these together we just get 4. So we get that y equals minus 1 on p x plus 4 plus 2p squared. Now I didn't want to put that in the general form because that will be the y-intercept for part 2. Okay, so we straight away know what the y-intercept is here there in part 2. So that was part 1. So in part 2 we're simply going to get the coordinates of Q are 0, 4 plus 2p squared. Right, now in part 3 we've got the point P, which is 4p 2p squared, the point Q, which is 0, 4 plus 2p squared. So the midpoint is going to be, add that and that together and divide by 2, you get 2p, add that together and that together, and that will give you, divide by 2, you'll get 2p squared plus 2. Okay, so now we need to find the Cartesian locus of that point. It's in parametric form, so we'll say x is equal to 2p, y is equal to 2p squared plus 2, which of course means here that p must equal x over 2. So substituting that back into this one, y equals 2 side of x on 2 all squared plus 2, which gives me y equals 2x squared on 4 plus 2, which is y equals x squared on 2 plus 2 is the locus of M, which is another parabola. Oh, number 2. The tangents at the points P to AP squared, and Q to AQ squared on the parabola x squared equals 4ay meet at T, and the normals at P and Q meet at R. Part 1, find the coordinates of T. Part 2, find the coordinates of R. Now the tangents meet at right angles. Prove that RT is parallel to the axis of the parabola. Okay, now pause the video. Have a go at this one. Okay, now what I think we should do is to draw a diagram of this. So first of all, we'll just a little sketch here. Okay. Remember, it doesn't have to be that accurate, but just so you can see what's happening. Okay, there we go. There's our parabola. So a different colour over here. So I've got a point here and a point here. Okay, I've got a tangent there and a tangent there. That one's the T. Okay, we've got another one up here. Right angles there, right angles there. That's R. Another different colour here. And we've got to show that RT is parallel to this axis here. Alright. Okay, first up, let's get part 1 done. Now what I'll do here, I'll actually just write down the equations of the tangents without deriving them. So let's write down this P and over here. This is P over here, isn't it? That's Q over there. So at P we have y equals px minus ap squared. And if you're not asked to derive this, you can just quote this. And at Q, y equals qx minus aq squared. So px minus ap squared equals qx minus aq squared. You remember doing this earlier on. So we get px minus qx equals ap squared minus aq squared. That's x outside of p minus q equals a outside of p minus q, p plus q. So x equals a into p plus q. Okay. Now, putting that back into this equation here, we get y is equal to ap into p plus q minus ap squared, which is ap squared plus apq minus ap squared, which is apq. Therefore, T has the coordinates a into p plus q, apq. Right, now to find the coordinates of R, we need to find the equations of the normals. So we'll just do that. So, part 2, we have y minus ap squared equals negative reciprocal of the tangent minus 1 on p into x minus 2ap. Okay, now I'm just going to expand it out. Minus 1 on px. This becomes plus 2a. So y is equal to minus 1 on px plus 2a plus ap squared. And similarly, because we just got a different parameter q, for the other one we got y equals minus 1 on q x plus 2a plus aq squared. Okay, now solving simultaneously, just write that as minus 1 on p x plus 2a plus ap squared equals minus 1 on qx plus 2a plus aq squared. And of course we note that these go out and we'll get the x's together. So I'll have minus 1 on px plus 1 on qx equals aq squared, taking this across the other side, minus ap squared. So that becomes x outside of 1 on q minus 1 on p equals a outside of, this will be q minus p, q plus p. And of course this becomes p minus q on pq equals a into, now that's a q minus p, I'll write that as a minus p minus q there, that's a p plus q here, and then we can see these p minus q's will cancel out, and you simply get x equals minus apq into p plus q. Okay, now to get the y one, so y is equal to, now I'll put it back into this one up here, so that's minus 1 on q times minus apq into p plus q plus 2a plus aq squared. Because these q's will go out, and this becomes ap into p plus q plus 2a plus aq squared, which is ap squared plus apq plus 2a plus aq squared. Just tighten it up a little bit. That's a into p squared plus pq plus q squared plus 2. So the coordinates of r are minus apq p plus q and a into p squared plus pq plus q squared plus 2. Now in part 3 we have to prove that RT is parallel to the axis. Now if you look at the x coordinates here, of t it's a into p plus q, and the element is minus APQ into P plus Q. So they're very close. Now, if we look at the gradients of the tangents, we can see that for M1, for P, that's equal to little p. For Q, M2 is equal to Q. Now, M1, M2 equals -1 because these are right angles. Therefore, PQ must equal -1. So we replace this PQ in here with -1. So in R, this becomes just simply A into P plus Q and A into whatever that is. Because we can note straight away that the X value here is the same as the X value there. Now if this X value is the same as this X value, then RT must be parallel to the y-axis.